Hi everyone, my name is Dean and you're listening to the MLOps podcast. As you probably know, machine learning in general and data science are two fields that are evolving all the time, and it's really hard to keep up to date. Specifically, the area of bringing machine learning into production or into the real world seems like it's very confusing. There's a lot going on and it's hard to make sense of all that's happening around you. But on the other hand, there are a lot of smart people that are doing great work in bringing their own projects into production. And we've had a chance to speak with a lot of these people, but it definitely seems like the information is not widespread enough and a lot of people don't know of best practices and how other teams work. So that's why we decided to start this podcast, where we'll be speaking with people who are working in various types of machine learning teams and hearing about how they are bringing their projects into production. I hope you find this interesting, and let's get started. Hi, everyone, and welcome to the MLOps podcast. I'm your host, Dean, and you're listening to the episode with Laszlo Sragner. Laszlo holds a master's in computer science and studied for a PhD in nonlinear modeling. He was a senior data scientist at King. You probably know them as the creators of Candy Crush, which was later acquired by Activision, which has recently been acquired by Microsoft. So a data scientist at Microsoft by proxy. He later co-founded and was head of data science at Arcera, which used machine learning to generate market intelligence for investment banks. And he is now the founder of Hypergolic, where he consults on ML topics. He applies the experience that he has to help companies build better machine learning products. He also, on a personal level, he has a really great blog and Substack, and is a well-known voice in the MLOps community. I first got to know him by reading a lot of his very interesting opinions on a lot of matters related to getting models to production. So he, in many ways, is a natural guest of this podcast, and I'm really happy to have you here, Laszlo. So thanks.
Thank you very much for your introduction, Dean, and I'm very happy to be here. You and welcome the audience as well.
So yeah, thanks. And I guess we're going to call this episode "Getting Data Scientists to Write Better Code." So let's start off the top. Why is it important that data scientists write better code?
Yeah, it's an interesting question because you are surprised how overlooked this is, both in studies and both in production or in the industry. My intuition was that software engineers are much better at this, and you know they seem to have less problems with the same issues what data science are suffering from. And I always thought that people should be proud of what they are creating and reuse what they created, and writing better code helps you do that and helps you structure your work better and have a clearer path to products and then to solving your problems.
Mm-hmm. So I guess if I'm a data scientist and I'm convinced, right, I want to write better code, and I think in many senses it's net positive. Who doesn't want to write better code? How do I actually go about doing that? What would it mean for me to improve my code writing abilities?
Yes, the first step is it's not an easy task. I must admit that there is very little literature of applying software engineering principles to data science. And that's one of the reasons why I write so much about this, because I'm in the position that if it's important for you, and it doesn't exist, then it is up to you to make it. So I write about this. I read a lot of content. I go to meetups where software engineers are discussing codecraft, and I take ideas from them based on first principles, break it down, why they are doing something. Does it apply to machine learning and data intensive situations, and then bring them over and then preach about only the parts which are relevant. The first very important thing to identify is data science is a statistical phenomenon. You are answering statistical hypotheses. So usually you are dealing with a large amount of data, and that's not necessarily true in a lot of software engineering principles. The first thing what you need to understand is code quality is about testing, and you need to build a testing capability. There is no refactoring without testing, and there is no code quality without refactoring. I think these are like the core principles. The question is, what do you mean by testing? And it usually just means, my code works. I have an input, I have an output, fix this, and then change the code. This is refactoring. So refactoring is changing your code to do the same thing, but in a nicer way. And then keep refactoring it, and then progress towards a place where you can read it better. And there are rules of what does it mean to read better, like a code to read better.
Mm-hmm. So I guess like you raised a bunch of points that I tend to agree with, and one of the things that we do when we speak to data scientists or even developers, you give someone a task, and then let's put this in the context of like job interviews, right? You give someone a task and they need to solve it or suggest a solution for it. And then usually the next question that we'd like to ask is like, okay, so what do you do now? Like you propose a solution, and then the answer that you expect is like, we're going to write tests to make sure that what we actually propose can work, will work. But do you think that there's a good starting point? Like there's obviously a lot of different types of tests that you can do. Where do you recommend starting?
Yes, that's an interesting question, because that's TDD, isn't it? It means that test-driven development, that you write the test first and then write the code. But I'm not sure whether that applies to machine learning, because you kind of need to create the model, see that the model works, and then review whether you did the right thing, you have the right features. And I also would take a step back, because it's not necessarily the machine learning part where you acquire most of the tech debt, but all of the glue code. And I think that from that Google tech debt famous article, that there is a lot of glue code around machine learning. And I think if you take care of that helps a lot. And then probably the modeling part is not that big of a problem. So I usually recommend to just have something out of the door. You have an intuitive feeling that you are converging in the right path. And then after like a short period, you start to have a better feel of the problem. What are the difficulties? What kind of data models do you have? I would like to have this in a class, what kind of services this provide to you, and then start converging to something that is a solution that will be easier to finalize. Because as you progress forward, you need to update it. And I think it's important to understand that tech debt will generate inevitably, just purely because you write code. And then the important part is to go back and refactor it and then get into a better state, and then periodically pay your debt. Does it make sense?
Yeah, it makes total sense. I think this also relates to something that maybe you and I discussed in the past, or at least I vaguely remember talking about this with someone recently, where if you assume that you're going to have to iterate on your code, and there's no chance that you're going to just write something, it's going to work, and then you're never going to revisit it, then not being afraid of the code you write becomes much more important, because you need to assume that you're going to have to understand the things that you created and modify them in the future. And so all of this code quality stuff sort of either pays its dividends or comes back to bite you in the ass if you didn't do it.
Yeah, it's a very good point, and you raised an important issue, which is the primary red flag. What we identify that you need to care more about your code craft, and that's what you mentioned, that I'm worried about changing my own code, and I break something. If you are in this state, you almost certainly need to think more about your code craft and write better code. And then it suddenly became a different question, because we talked about testing, and that has different layers, because you have hypotheses about your code base. It's like it does some kind of function, and if you change it, you would like to test whether these hypotheses still stand. But there are ones which can easily broken and easily tested, and these should be taken care of by an easy test. Like you make a typo somewhere, or you leave something out and you get into an invalid state. Just write something that runs in 0.1% of the data, and run the pipeline in a couple of seconds, and then you start having this iteration, because then I can change my code and check whether I did the right thing in 1 second or 10 seconds, and then if I did this, I can use the same pipeline on 10% of the data or 100% of the data in an hour, run it again, and now I have confidence that it's probably not going to be a waste of time, because I just checked my code syntactically, and I get feedback. And then you start building this kind of habit of being progressive about your own code and not worrying about restarting and running code.
Yeah, I couldn't agree more. I'll just share a concrete story just from last week. I was talking with a friend who's a data scientist about scaling up a model. Like, he's working on a data set that is a few tens of gigabytes, and it's a personal project. So he doesn't have a ton of resources, and he doesn't want to do a ton of training on the entire data set that might be very expensive without making sure that it will work before. And so the first advice was like, okay, take 1 gigabyte of data out of the huge data set and run the pipeline end to end on that subset of the data and see that it actually runs. Like, maybe you'll discover that it fails just before the last batch. And if you would have done that with 40 gigabytes, it would have failed on the last batch of that, and then you'd waste a ton of time. And that also will give you, and time it. So you can also say, like, okay, I know that one epoch on 1 gigabyte of data is taking me X minutes. So I'm assuming that if I multiply that by 50, it's going to take me roughly 50 times more. Maybe not, but it's going to be the best initial estimate that I can make. But the other interesting thing, which relates to what we were saying, is if you assume that that's the correct approach, that you're starting with a subset and then you're going to expand, then you're going to write code that will let you later expand to the rest of the data set. So your approach to writing code is, I'm not going to hard code everything so it only works for 1 gigabyte, and then I have to rewrite all the stack for the full data set. But I'm actually thinking about the fact that this is a subset and it's going to have to grow. So it's sort of develops the proper way of doing things by trying to create smaller experiments that you actually want to run. So yeah, I think this is a great practical point that people can take. I guess I'm also interested in, like, I shared a bit of your experience at a high level, but if you can share what part of your past experiences led you to the conclusion that better code is important to strive for?
So I think I left from my bio that I was working in finance for a long period of time in around the great financial crisis. And the first thing what my boss, who was a hedge fund manager, said that, Laszlo, the model you write is the model we will go into trade on. And it means that, it's the code you write will going to be used forever. So it means that there is not going to be another person who translates your code. So you need to write in a sense that you can be confident that your model works well, and then you can be sure that it is easy to move to production. And I think that was one of the key aspects, and I think that breaks down a lot, is that the POC, MVP, and productionized steps create different quality solutions, and that slows down translation from one step to another. Too much friction is to move from POC to MVP. But if you maintain code quality, these separations are blurred, and you have a much easier path to MVP or production. You don't need to retranslate code, because there is another aspect of translation that is harmful, is that you are building quite a lot of know-how about your code, which is you are writing it in a fashion that is not really translatable. But if you are maintaining this code to production, the person, even if he is not going to be you, maybe you are going to be you in 6 months' time, but if not you, that person can take a lot of your knowledge through the well-maintained code and has an easier time to production. So that's an extra benefit. And I think because a lot of projects fail because of the tech that they accumulate during the POC phase, but they don't believe that they are close to a solution, because they they are fighting tech debt very early on. And I think that's probably lowers the risk of ML projects if they maintain code better, because they have a clearer path of understanding that they can reach some kind of production stage easier.
Yeah, I obviously agree. I guess I'll ask a question for the people that maybe disagree with us. Like, how would you prove to someone that the overall effort is lower? Because what we're basically both agreeing is that if you invest time upfront in making your code quality better, you're going to save more time than you put in by lowering the friction to productionize it, by increasing the success rate of your projects and things like that. But if I'm a cynical data scientist who doesn't want to write high quality code, I might say, listen, that's what you're claiming, but I'm actually going to put in 10 times more hours into improving my code quality. And at the same time, I could have just deployed 10 models. So yeah, how do you respond to that?
Yes, first of all, obviously, we are not doing this in a vacuum. Just because we start, software engineering has like 20 years of experience with productionized code, and they figured this out. So that I always refer to this, that some of the principles that are working for software engineering and translatable to machine learning, we don't need to argue about that, because that has been proven to be correct. The parts which didn't, especially that relates to statistics and the data-driven nature of the field, that's a different question. So that's point one. The second point is the amount of effort that is put into maintaining a code base is widely overestimated. That's actually not more than 10-20%. If you are starting, if you are practitioners, that's the way you do it. You have a better way to estimating of how long things will gonna happen. You have a better way of chopping it up into smaller places. As you mentioned, you have a more granular estimation. So your friend's example about the 10 gigabyte, 1 gigabyte, that's exactly what we are using as well. Have a partial productionized problem, have a more transparency on your overall problem, and then use that as an estimation point to scale it up to the whole system. So I would think that there are so many positive points. Obviously, it would help if we progress forward with this project or this paradigm, and there is going to be use cases which I'm going to be certain that we're going to blow everyone out of the water. So, and we're not going to have this conversation in about 2 years.
Yeah, I think that last part is super important in its early days. But I feel like that's also like the first thing that you said is something that we also rely on. Like if you break it apart and think about this from first principles, then the data science or machine learning is built on some components that are already people thought about and solved hard problems for. One of them is code. So you could argue that is sort of already solved, and it's just a matter of adopting the workflows and the tools and everything and sort of fitting them to the needs. I guess data is the joker here, right? Because you could say like data engineering is something that also works at very large scales, and you have all these databases that are incredibly complex and are maintained in production and things like that. Something in the communication between them and adding statistics and learning into it is, I guess, the final frontier that we still need to prove. But yeah, go ahead.
If you think about the same process happening in databases as well, the data engineering with DBT, that's a classic example. They are essentially inventing the CI/CD for databases. So I think that's a general zeitgeist issue here, which is everywhere is happening, because everyone is recognizes that Git flow is the way to go, or Git-like processes. And there is another important issue which I would like to emphasize here, is that often companies adopt Agile, Scrum, or some kind of agility methodology, and it doesn't really work. And I was looking for answers of why people are resisting this, and usually the answers is data science is research. You have high risk projects and stuff like that. But I think one of the core issue is because data scientists are not thinking about projects as a programming task, it's much harder to break it down to smaller chunks. And therefore, it's harder to estimate because it means that essentially the entire project becomes one ticket, and that's not an estimation problem. You need to have a very good idea of, and every project built out of risky components and engineering components, and then you would like to see at least the engineering parts to be sequenced and deterministically executed. Maybe you can even outsource that to a team member, which you can do if you have a better compositionality in your project. And you can flag risky tasks where it's not success what you are looking for, but an answer to your hypothesis. And then you can throw it away if the answer was negative, and then you can just sequence, and having a better understanding of how much a hypothesis need to be answered, like time boxed, because that's the other question is often you're thinking about time boxing, but how do you time box an open-ended data science question? You are essentially going to stop at some point and not, having a conclusion.
Yeah. Yeah, I think I gave a shout out about this in one of our other episodes, but there's a really good YouTube video. I'll link to it in the description of this episode as well, by a guy named Dima Goldenberg, who's data science team lead at booking.com, where he speaks about applying agile to data science projects and the challenges there. I think that the two interesting points that are actually actionable and you can do them tomorrow is, one is, like you say, like, yes, you need to spend a bit of time flagging what's risky, trying to define like what would be a result that satisfies you to define as negative or positive, and what would be the next steps in each case, and how do the rest of the tasks that are maybe not as risky or not as data science related, how do they play with the different result options? And then the other thing, which is even more technical, I guess, is if you think about your data pipeline, and when I mean data pipeline, I mean this in I guess maybe the more correct term is machine learning pipeline. But what's the steps that your data is going to go through from the input that you're getting from someone else to the results that you're looking for? And if you build that into steps, whether it's using one of the data pipelining tools or just writing it on a piece of paper, that many times provides you with a good framework to break things apart. Say, like, we're only going to work on this node of the pipeline. We're going to see that we can get some result, and then we're going to move on to the next node. Or rather, we're going to work on the entire pipeline, but on a very, let's say, basic level, and then start improving nodes as we see results coming in. I guess one follow-up or one general question that I have is, obviously, taking machine learning models to production is a very broad topic. I'm curious to hear, sort of from your perspective, what's the most interesting part or the most challenging part of doing this?
Yeah, it's an interesting question. How to phrase it in a way that is matching to the topic of the podcast. So I voiced this several places that, despite the Google's tech debt in AI diagram, that there is a lot of content outside of modeling, I do still think that modeling is the core part of machine learning. Mm-hmm. But it essentially to solve the other parts correctly, and that's one of the reasons why I advocate high quality code and code crafting and good project management around this, is because that allows you to spend more energy on modeling, and I think that is the ultimate crux of the thing. If you're organized everywhere else, then you can focus on the hardest part, which is clearly modeling. And there is we have a general methodology of how do we approach modeling, especially new places, because we often face with completely new domains where we need to onboard ourselves, in terms of embedding spaces, deep learning models. How do you frame the input output data in a way that you know that it's going to create a problem that is easily to modelable. And then you can answer questions about, next steps, what kind of extra features you bring in, what's your hypothesis that is going to help you. And that allows you to if your code is written in the right way, you can relatively easily test these hypotheses. And I think that's the best way to think about modeling. But I do spend most of our energy is spent in modeling and talking to clients, evaluating model results, because productionized models are always like facing the world. The world is a messy place, and there is always like edge cases and new situations, and there is a lot of feedback. And one of the biggest problem in machine learning, especially productionized machine learning, is how do you incorporate feedback? How do you while still keeping what's going on in what the hypotheses you have already proven. You don't want to break them, and that's why you need to have like a disciplined framework, or you're just invalidating your previous assumptions.
Yeah, I guess connecting sort of the feedback back into the loop, the technical side of that is like monitoring the model, monitoring the data, trying to see if there are drifts. After you discover one, then there's the other technical part of how do I get samples that represent the change in either the data or that are causing the changes in the model results, and then sort of tie them back into the data set that I'm training on or using for the development part, so that the next model is sort of better. And I think we already discussed on this podcast, like model forgetting, catastrophic forgetting and stuff like that. Like, how do you add a subset of samples that are problematic without losing the performance on the main chunk of data points that you started with? I guess, when you say that modeling is the hardest part, do you mean also the parts that I just mentioned, or are you still referring to, let's say, the even more core part of modeling, which is like, how do I structure this problem so that a machine learning model can actually learn something and perform a task?
Yes. The modeling part is, there is this concept of accidental complexity and necessary complexity. Mm-hmm. And models are necessarily complex. They are hard problems. If you describe like real life events with like algorithms, that's always going to be a challenge. I think the organization is a question of like accidental complexity. It means that it's hard because you didn't get it right, mm-hmm. and then you need to practice and figure out of why you are slow, what doesn't work, and how to create the right processes to maintain this. Currently, there are not too much paradigm around this. I mean, agility and lean and iterative machine learning is one paradigm, but it's very rarely practiced. Mm-hmm. And also, you mentioned that monitoring helps, and data drift and other issues, but these are statistical impacts. There is productionized models have another impact, which is like just users coming in and complaining of, why do I see this in the recommender system and why do I don't see something else? And answering these questions are also a source of feedback to the model. And then you need to walk away and then estimate of how many other people see these problems, and then what I'm going to do to fix that. What's the cost of that, and how do I make sure that while I'm fixing it, I'm not breaking something else? And I think these are all process questions. If you are fighting your code base and you are worried about changing it, you are going to have a bad time. So that's what one plus point again to code craft.
If you're trying to solve hard problems, you want to make sure that everything which shouldn't be a problem is not a problem, so you can focus on what really is the hard problem. I guess, if you have an example, can you share of an organization or project that you saw do this well, and what was like the eureka moment that solved this issue?
I can talk about our previous company. Probably that's the one I'm most familiar with. So we were processing maybe about 500,000 articles a day from countries like Egypt or Turkey in a foreign language no one speaks in the office. Auto-translated it, selected the relevant ones, which is again a big question of which one is relevant. How do you define relevance? From this 500,000, maybe 50 a day, and send it to traders at major investment banks, essentially trying to find articles that are relevant for trading, equities or debt in these countries, and changing the decisions how they are doing this. And that's an extremely hard problem, because you need to go from 500,000 to 50. It means that how much is 0.01% of the success rate. It's very hard to have this precision in an NLP pipeline. And this is why, meanwhile, you have 3 data scientists, plus me. So that's not exactly a large team. And this is exactly why we needed to be organized. And we know that we need to progress in a way that we are building, a structure that we can reuse efficiently while still maintained by 3 people. And one of our core principles was that every model was deep learning models. So essentially, when we get the user feedback, which is usually like a human in the loop situation, we were able to build an ensemble in this deep learning model and then ship this model as if nothing happened, because obviously the engineering team didn't know that we updated the model because the input-output interfaces were the same. And that was our secret sauce, that we were able to ship new models because we used TensorFlow as a programming language, and we were able to update our models. And we had a very strict data lineage. So it means that every transaction or every API calls and everything was logged with the model version that was involved in these decisions. So we can trace back whether, if you have a model in production, or maybe more than one model in production, which one was the one that created the situation that a user complained about, because that's what you need to do, because we immediately was in the situation is we started to get confused that we fixed the problem in this pipeline, we ship the model, but in a microservice architecture, it takes some time until this updated, and an error came back. We need to know immediately that we already solved this problem. Otherwise, you are continuously keep checking yourself. So you need to have a lot of organization and accounting to make sure that in an iterative process, you always know that you are doing the right thing, or check things off your to-do list.
Yeah, sorry. That is really interesting. I'm actually very curious about the whole part of deploying a model to production without engineering knowing that something changed. I feel like many of the listeners are going to be like, what? That's possible? How did you get that to actually work?
Technically, they do know that we have a new model, because we needed to send them an asset which is going to be deployed with the Docker containers or TensorServe, I think. But if the input-output wasn't changed, and a natural language processing model is a very internal issue, because you have text in the output and then some kind of labels on the text in the input and some labels on the output. But inside is where the magic happens. So usually you don't really need the data science, the engineering team to change anything on their side, and you can ship another model. And I think this was a particularly NLP focused thing. Probably if you deal with structured data a lot, where the features have more crucial role, then you can't do that easier, but you have feature stores and other solutions for this.
And then the second part is, you said that you would create an ensemble of models and you would modify that according to your human in the loop input. Does that mean that your approach to the ensemble was that you chose the weighting and the models that were within this, or was that automatically selected somehow?
Yes. So the ensemble, TensorFlow is a programming language. You can write whatever code you want. If you want to have fixed weight between ensemble components, have fixed weight. If you want to train them as well, you can do that as well. But usually what we found is we had a core model, and then applying like real CI/CD in modeling. We only added a small ensemble component, which was trained on a specifically selected data set, which were capable of modifying the output of the model, but not radically, because for certain situation, what you want is everything should stay the same, but the problem which you are focusing on and you get the feedback from should change a lot. And then you can run a large pipeline and you can evaluate that, yes, the model didn't change for most of the situation, just the critical ones where I want to happen. So this was the model. So the model worked automatically, and the domain people who were like financial analysts were downstream from that, who were making decisions of, I'm seeing articles that I shouldn't see, or we were missing something, and then they were one of the major source of feedback, because clearly the traders are not going to call you and tell you that, sorry, you missed an article. Sometimes they call you. You are already in very big trouble if they call you.
Depending on how much money they lost. Yeah. Exactly. Do you think that there's a major difference between doing all of this, like writing better code, but working in a more structured way for small startups compared to large organizations? Because obviously there's more constraint on resources when the smaller the company is. And also there's a mentality shift, right? Like when you're a very small company, you might say like, we only want to focus on what's most important, and we can focus on code quality later. Like, let's start by writing everything in one notebook and worry about code quality when we have 1 million users.
Yeah, it's an interesting question. I find that data scientists who are working in large organizations usually have a much stricter way of doing things. Like, it's a restricted way. It's almost like low code programming, where there has a it's called a golden path. This is the way we do it. And this is what it takes to have an XGBoost model and features in production. So I would think that probably they need to worry about less, because the constrained environment will gonna push them to having a certain structure which is easily understandable, because that's what you try to achieve, is like, I have some project 6 months ago and I still know what it does, or I can catch up quickly. Yeah. It's different situations in a startup where they usually face a new problem. They usually in experimentation mode. I do think that it's a fallacy to say that we shouldn't worry about code quality early on because we want to move fast. I don't think that is true. Like, you are you are not going to move faster. This has been proven by software engineers that code quality does make you faster in the short term, in any sense. In the short term, in the long term, less stressful, less frustrating, more productive, and so on and so on and so on. Kent Beck has a video on extract, expand, experiment, or something like that, 3 X's. And if you watch his argument, the code quality is a positive feedback on all 3 of the stages. What you say about startups is that they are in the experiment phase, and they need to move fast, which means that you are almost certainly in a frequently changing environment. You want to make change easy, and you make change easy by caring about your code quality.
I like that. We'll add the link to that as well. It seems like something that could benefit a lot of people. So let's try to maybe take this to an even more practical level. Can you walk me through your process for thinking about a problem that can be solved with machine learning? When do you start actually writing code, and how do you approach the first iteration?
Usually, like, you have the traditional steps of exploratory data analysis, POC, MVP, A/B tests, productionization. And I think these are good, mental states where you are. exploratory data analysis, very quick, just to get a feel of the data, try to move. The first step, what you need to establish is a domain model. What are your nouns? What kind of properties these have? How do you describe your data? Usually you are in some kind of business case. You talk to domain experts, and they will gonna speak a language, and you use that language in your data. And that's the first step. So you start converging. You start with a data domain model, and then you start moving into processing, because you need to filter this data. You need to understand what it does. What's the statistical properties? What are the big issues? What you need to ignore? What else do you need? And converge towards a data set which is understood. So that's usually around POC stage, because at that point you start thinking about, okay, what kind of steps do I need to do to clean this data in production eventually? And I start writing like classes of that, which can turn into services, that can turn into features. But I start maintaining my understanding of the data and what should happen in the future, while having a refactorable pipeline. And this is going to last until you are in some kind of MVP evaluation stage, where you start thinking about, okay, I have my model, I have my processing pipeline in a relatively abstract way. Now let's scale it up. An MVP usually is done on a relatively large amount of data, but my domain model is in a state, my processing pipeline is in an abstract state, so I can take them over to some kind of pipelining tool, some kind of scalable tool. So I'm helping myself all of this path by always maintaining some level of quality, but by enabling myself to smoothly move to the next phase. And I think that's very important, that you don't really say that, okay, next week I start to think about MVP, and I'm already regretting it because I need to rewrite everything from scratch, and nothing will going to match the previous state. So I'm going to debug code for days because I make some kind of assumptions that not true in the productionized environment. And I think this is important, that you are always in this kind of path upwards. And the MVP stage is where you need decisions about, is it a partial solution, what we talked about? So we usually advocate some kind of vertical slice, which means that try to scale down your problem, but in a vertical slice, so end to end. For example, in our example, we had about 7-8 countries. We started with one. Let's do one, and then we see end to end, and we will going to know how much labor data we need, what kind of errors we are going to have, how much is going to take us from getting a new country, or getting 10 new countries, 100 new countries, and you are much better positioned. But obviously that start to be like project management. And obviously I didn't speak about the modeling part, but that is on its own. You can apply these principles because eventually that your model will be in production.
Mm-hmm. I think that one of the interesting points that you made is sort of the way in which you minimize the problem to a vertical slice. It might sound trivial, but I think in many cases it isn't. If in your example, you were talking about countries. So sort of you could argue that there is a level of cohesiveness within the data that comes from a single country, which might not be as similar to another country. So minimizing it down to one country is like a logical component of the model that you can work on end to end, and then expand it to other countries. I think that from like the example that I gave earlier, where you have a huge amount of data and you decide to just use a subset of that requires, I guess, more care, because you need to make sure that you're not minimizing to a subset that is maybe not representative or not cohesive, and then you might not be learning the correct things, and the expansion would be problematic later. So do you have any tips on how to do that?
Yeah, it's a very good point, but like that's our job, it's if you are in charge of a productionized problem, It's your job to understand it at the level that you can, where is the slice, I can slice it off and I can help myself and tell my boss that, this is a $1 million 3-month problem. We will going to need 20 people to do that, or maybe just 5 people, or we can sequence it all over. And you can start building this transparency if you can understand that. If you want quick tips, usually categorical variables, that's where you start looking at, like quickly I was thinking about like Yelp reviews or some kind of text processing in Yelp reviews, like pick one town, how big that town is, you pick San Francisco, a couple of million people, fix that, how quick, expensive you're going to be, scale it to, New York, or adding, 20, 1/20th of the size of San Francisco towns. And then you start thinking about having a more thoughtful understanding of the problem, while obviously the reason why you usually don't reach this level, because you don't really have time to think about this, because what you are worried about is like changing your code. You need to rerun a pipeline on only a subset of the data, and then have some kind of descriptive statistics. It's not easy if your code is in a certain state, but usually these issues coming out in the planning stage, or at least at the EDA stage, where you are having a better understanding of the problem, and you do need to have a roadmap. And this is exactly where that agile roadmap comes in, that you are capable of breaking it down into smaller steps, both from the project point of view, both from the technical point of view, and both from the roadmap point of view, because that's what you are communicating to your boss, because he's going to, you don't want to be in a situation that we are working on it in 6 months, and then you say, I don't know what's going on, we failed, that's not transparency. You are going to be in a trouble.
Yeah. Yeah, that's an understatement of the year. Transparency and communication is obviously important, and I think that basically the point that you're making that I very much agree with is that they are very tightly tied into your code quality, because that enables you to minimize the project to something that you can easily communicate success or failure on at a short time frame, and then build incrementally on it. I think that maybe an overarching takeaway from this entire discussion so far is that machine learning projects and data science projects can be broken apart into smaller, more manageable problems. You just need to put in the sort of the thoughts and time into doing that before you get started. And then you need to write code that supports that breaking down into smaller problems. I guess I want to ask you a few, take a step to the side and ask a few questions that are maybe not as related, but just curious to hear your thoughts. So the first is, there's a huge debate in the community, you're probably as exposed to it as I am, about end-to-end platforms versus the best of breed tools. Which is best and when?
Mm-hmm. Yeah. I think it's too early to tell. I was just recently having a conversation with a founder, and he was saying that not enough people are doing machine learning, just because in production. Mm-hmm. And I think it's a lot of these early stage companies need to, machine learning as an industry need to grow mm-hmm. larger before we're going to crystallize some kind of standard way of doing things, and then product which we are going to match with that, we're going to be better. But I think we are simply not there yet. So often, low-level tools are too low-level. So data scientists are not great programmers, as we just discussed this whole episode. It means that they are struggling using them, and I think maybe that's one of the reasons of the machine learning engineer as a paradigm, who are essentially engineers and they don't do machine learning themselves. Mm-hmm. It's a bit of a misnomer. Working there, because the data scientists who are statisticians are simply, this is two different paradigms. They can't, you can't have it at the same time in your head. Layers of abstraction is one of the most important system design architecture, and often I feel that in the current paradigm, data scientists, people who are dealing with data drift and such and modeling, expected to learn Docker and Kflow. And I think these are not on the same abstraction level, and we know that this is not going to be a good experience. And best of breed tools usually, I feel they are restrictive. So because there is no standard way of doing things, they are solving one problem. If you have exactly that problem, that's the best solution. But if you don't have that problem, then what? It's like, okay, I use this, but I also need an alternative route where I solve my own problem. Then what's the point?
Yeah, I understand. I guess it's interesting because I feel like part of what you're saying has implications for the future of let's say job titles in the field. I think ML engineers, when we started DagsHub, was not really a thing. Like some people had the title, but it wasn't clear if they mean like ML researchers that have a product under their wing or something like that. Today, I feel like it's getting closer to the way you define it, where it's someone who understands machine learning processes, but is not actively working on machine learning, instead working on like the infrastructure or tooling or connecting the tooling for machine learning projects. And it's a big question of, I guess, like my question here is like, what do you think the future holds? Do you think that the ML engineers are going to take more of the roles of the statistically oriented data scientists and sort of combine that under one roof? Is it going to go the other way? Or is this or do you think that this is going to remain this way for a long time?
Yeah, I think it's a good analogy to look at what DevOps and software engineering has. Like you have front end, back end, and DevOps, but you have site reliability engineer, which is somewhere in the between of the second two. And I think there is going to be some kind of similar convergence. I personally don't see that someone who deals with customers, product managers, and machine learning models will going to deal with Docker containers and Kflow. Someone else needs to do that. And I don't think that it's a good concept of what was the way? It's like you ship it, you own it. I think that's just saying data scientists who are not equipped to this tool of you are on your own. And I don't think that you should run teams like this. You have a problem. Machine learning productionized machine learning requires a set of skills that doesn't need to be in the same person. So you can have good machine learning engineers, you can have good MLOps engineers, you can have good research scientists in the same group, like collectively. And it's the leader's job to organize them and make sure that all of the roles felt, important. I suspect that one of the reasons why it's called machine learning engineer is to entice people to go into this area, because it has nothing to do with machine learning. And I'm always worried when someone comes into an MLOps community and say that, I just learned about NLP and I would like to learn more about MLOps because I want to be a machine learning engineer. And it's like, you just learn about natural language processing. You do understand that MLOps has nothing to do with NLP, and I think that's important, image or branding problem.
They do have the thing in common, which is that they are both acronyms. So it might be confusing that way. I would say just to play devil's advocate, I'm not sure I completely agree. I think that a lot of times, like in smaller teams, you do see what is sometimes called a unicorn, like someone that can do everything. And they're pretty good at it. So you feel like, oh, well, if I can find one person that can do that, then there's probably an army of people that can do that. I just need to hire them. I do agree that like when you grow, the sort of the thing that makes humans great is that we can specialize. And so having everyone do everything is probably not a good idea beyond a certain size. I will say that like on a personal level, I do encourage data scientists to at least play around with Docker. I definitely don't think that they should be Docker experts, but they should, in the same way that I feel like even if you're a developer and you're not a DevOps person, you should understand a bit of cloud. Then I feel like there is a value in data scientists understanding their surroundings, but I agree with you that they shouldn't be Docker experts or something like that.
Let me clarify myself. I didn't say don't know what Docker is. I felt that usually, like in a productionized environment, understanding Docker to the minute to the same level, for example, you understand, let's say, an NLP model, what a Hugging Face model built up, and you can actively contribute to it. So there's like a very high level of involvement. I don't see that you can do the both at the same time. Yes, you have unicorns, but unicorns are very, very rare, almost non-existent.
Yeah.
You radically reduce your hiring problem, personal growth problems, if you are capable of building a team that are built by people who doesn't need to be unicorns, because maybe I can find them in the street, and I don't need to worry about top schools, because that's the problem, is like you are competing with Facebook and Google for these people. So you do need to be like what I can use to describe as a Moneyball situation. If you see the film, you need to merge those people in the team. And one of the things what helps, if you have a team with like diverse skills, that they will gonna cross-train them after they are in the job. But you don't hire people, you're solving problems, it's like their well-being is like, I don't want to be cruel about this, but secondary, it's like your problem is solving the problem. It's like it's a great thing that you can create a positive team environment, but your primary goal is how to solve this problem cheaper. And I think diversifying the team and then building a good team culture and shared culture is a cheaper way to solve a problem than hunting unicorns.
Hunting unicorns is probably a bad idea in general. I like that. That's a hot take. I understand what you're saying. I think that the cross-training thing is very important, and I think people underestimate how effective that can be. If people, I guess you want to hire for that trait of people being willing and being patient enough to share their knowledge with other team members. But that is more common a trait than being a unicorn and being good at everything. And so if you can hire for a very, very strong skill set in one domain with the ability to share it with other people, then you're going to have a team of unicorns in a very short time period that you grew, so you didn't need to hunt them.
This is a great take, because that's one of the primary goal what we're hiring for. When I was building my team, is like, you do realize you need to learn a lot on this, and then you need to teach others. So it means that this is a collaborative environment, and you can test these. Usually we expect you to explain your like, let's say you have a PhD in a certain fields, you need to explain to us of what you are doing, and that's an exercise of how good teacher you are. Like, you are an expert in this field and we know nothing about it, but we need to crank up our knowledge in this in like half an hour. What can you pass on to us? And that was a great way of seeing someone talk. And I don't think this is very like introvert extrovert thing. It's in a personal level, and it's not, you don't need to present yourself. And obviously you can help people who are more introvert to help the team in ways that are not harmful for them. But I do agree that cross training is very important. And as you said, it's like you might not hire unicorns, but you are making them.
Yeah, exactly. So the next question, and I want to be conscious of time. So the next question is like build versus buy. What do you think?
I used to say build and buy. There is, like, every machine learning problem is different. And I think the reason for that is because it's too close to the business. So it means that all machine learning problems are somehow business process problems, and that's company dependent. So you always need to expect to build something. I feel that currently the machine learning is very architecture driven, and that's why this is coming up. It means that you are thinking about architecture, components, bought or built. But there is another layer on top of that, which is the abstract layer where the problem actually is solved, and that is definitely going to be written. I think that's currently one of our main problems, and this is why we are advocating Codecraft, because this architecture-driven machine learning is partly the reason why data scientists are ineffective code writers. So they need some help. You have deployment problems if you don't know how to deploy code. You have feature engineering problems if you don't know how to write good features. Let's buy a feature store. So that's a dual problem.
Okay, that's a good answer. I like that. And let's finish with three sort of more personal questions. So first is, what in your opinion is the most exciting trends in machine learning and MLOps?
My personal favorite is graphical machine learning. So this is Bronstein and Veličković, I think.
Okay.
The second trend hopefully is code crafting and lean machine learning, and making the whole process more fluent and less stressful, and turning machine learning into a positive experience, because I think there is too much frustration, and removing that would turn this into a great field.
Those are great points, and we'll try to add more reading materials in the description if someone wants to dive into it on a deeper level. How do you keep up to date? This is very hard, but yeah, everything's going on in the field. How do you?
Yeah, I do think I'm failing in that, especially reading scientific articles, because we are now focusing on like product management and like code craft. That's not a particularly research field. I feel falling behind. I watch YouTube videos at twice the speed, so you can watch twice as much, and that's one of our major source. MLOps community, both Demetrius's and Chip Huyen's MLOps community. I'm getting a lot of content from there, and other than that, it's just Twitter.
Okay, so let's finish with recommendations for the audience, and it doesn't have to be data science related.
Okay, yeah, I think be prepared to learn more. It's important to understand that our field is very new, and there is no standard way of doing things, and it's probably going to change. And I think we all need to prepare that, changing our mind and learn new things and reinvent ourselves in the near future.
Awesome. Any books or I don't know Substacks that you're reading, except for your own, which we'll link to, which is really awesome, and I recommend it, that you recommend for the audience?
I recommend Martin Fowler's Refactoring. That's a very good book. I also recommend Gergely Oros's software engineering, pragmatic software engineer, or something like that. Substack, that's probably the top Substack at the moment. It has a paid version as well, but there is a lot of content for free. What else? Yeah, these are two good ones.
Okay. Any non-data science recommendations you have? Some Netflix show that you're enjoying, or
for my Substack, for the blogging, because my native language is not English, I spend a lot of energy on learning copywriting. So that's an interesting topic as well, how to write well and how to practice getting your point through in a blog post that's not accidental. And I think having better coherence around that is important. So maybe I'm gonna give you a couple of links privately.
Awesome. That sounds great, and also interesting to a lot of the audience. I think having to explain the things that you understand in a way that other people will understand will make you understand those things better. So I think that makes sense. I guess I'm going to give one recommendation in my spirit of giving recommendations which are not at all related to data science. I'm a huge nerd, and I started reading Ender's Game. I'm guessing a lot of the audience is going to be familiar with that. There's a huge series of books. There's the main series, which is called like the Enderverse Quintet, whatever. And then there's the Shadow series, which follows another character called Bean. And I recently discovered that the last book that ties the entire series together was published in November of 2021. And just to be clear, the first book came out in 1985. So it's been a long time coming. So of course I ordered it the moment I found out, and I just read it. it's nice to finally tie that together. So if there are any Ender fans that haven't heard of that, I recommend it. That's it, I think, for us for today. Laszlo, thank you very much for taking the time to speak with me. This was super interesting. I learned things on the fly, and I'm sure a lot of our audience will as well. And we'll share, there seems to be a ton of links to share, so we'll share them in the description so you can read more if you're interested. So thank you.
Thank you very much, Dean. Thank you very much, Dean. And thanks for the audience for their time. And I was very happy to be here. Thank you very much.
Great. Happy to have you here and see you next time. Bye, everyone.
Goodbye.
Thank you for listening to the MLOps podcast. If you enjoyed this episode, please like the video or subscribe. If you have any feedback, leave a comment below. Thanks again for listening and see you next time.